Hello, students. Today we want to talk about the definition of derivative. We've studied limits, we've studied continuity, and we've studied infinite limits. And these ideas are necessary to move into the definition of derivative and talking about that object because, of course, it's very important to calculus. So let's get started. Now, the preliminary definitions will not be surprising in the sense that it should remind you of a lot of the things that you did in your pre-calculus techniques. Now, one thing that you're going to notice with the derivative is the difference quotient. And that's something you talked about when you took your prerequisite courses. And again, a rise over a run, a slope of a secant line. And so in order to set up the notation here, we first want to start with the delta x differential. Now, we're going to have an alternative form of the derivative, which you can see down here, but I'll say a little bit more about it so you understand where it comes from. So the delta x will be a non-zero real number. Now, remember, probably in your prerequisites, you would use a letter like h, but the delta x is just a number. It's not two numbers. It just takes two symbols to write. And in many cases, the delta x can be termed the change in x. That's a common usage with the terminology. And so what we want to do is, and I've got here, C is in the domain of f, but you kind of see that from the definition here that that's tacitly assumed. But if we fix a C, a real number, and then we suppose f is a function, then the derivative of f at c is defined as the following. Now, we will have other notations for derivative, but for now, we're going to use the prime notation, just a little prime mark, okay? And it will serve us very well. So we're going to say f prime of c, or the derivative of f at c, is the limit as delta x approaches zero of the difference quotient. That is f of c plus delta x minus f of c divided by delta x. So that's a rise over run. Basically, you've got 2 points on the graph, okay? And you're taking the change in y over the change in x. That's what defines the secant line. And then, of course, if the delta x is approaching zero, then you're thinking that the ultimate result, if the limit exists as I've written here, would be the slope of the tangent line, because basically the points converge. And so you have the intersection of a line with the graph at one point. So geometrically, the derivative is a manifestation of the slope of the tangent line when that tangent line slope exists. And so in your mind's eye, you could think that we would need continuous curves, but they would need to have a nice shape. That is, smoothness would come to mind. And that characterization will actually be very useful for you. Now, before we move on to some other ideas here, which should remind you of continuity, I want to give you an alternative form of the derivative, which we will use quite a bit. Now, what we just defined was f prime of c, which was the limit as delta x approaches zero of the difference quotient, f of c plus delta x minus f of c divided by delta x. So the idea here is, just as we thought before, how can we transform this so we still have a difference quotient, but maybe a little less busy, and it's easily done. So we start with this definition, and we just set x equal to c plus delta x. So we set x equal to c plus delta x. And then if you solve for delta x, you simply get x minus c. Okay, so that's like a change also, but written in terms of two variables. Now, if delta x is approaching zero, in this case, then it must be the case that x is approaching c. Because this approaches zero, this must also approach zero. So we get a toggle like we had before in the previous lecture, which would say that delta x approaching zero would be equivalent to x approaching c. So now we can look at this form and switch everything out. Delta x approaching zero can be replaced with x approaches c. F of c plus delta x is now f of x. F of c doesn't change. And then, of course, delta x is x minus c. So we get a second form, which actually turns out to be primary in many ways because arithmetically it serves us much better. But there may be occasions when we'll go back to this form, but this one will be primary in a lot that we do. So now we have this alternative form, which seems very straightforward. That is the limit as x approaches c of f of x minus c divided by x minus c. And we'll come back to this discussion shortly. Now, not because this is kind of the linchpin of our existence, but you know, when we talked about continuity, that we would think of continuity on an open set and then continuity on a closed set, where we would have to consider left and right limits. Well, differentiability is the same way. So we've got a new word that I wrote here. When we say a function is continuous on an interval, we say it has continuity there. And then we're going to say when a function is differentiable on an interval, we say it has differentiability there. So just a long word that is synonymous with continuity. So if we think of I as being the open set A to B, then we could say the function f is differentiable on I provided this object, f prime of c, exists for all c in AB. Okay, and so we could think of, once we computed that limit, we could say, okay, f prime of c exists for all these c, like a domain of differentiability, like a domain of continuity. And then we could switch out the c with an x and think of the derivative as just a function of x. So we want to kind of pinpoint where the derivatives exist, and then we can treat the derivative at a point extended to all values of the set, replacing the c with x, and then thinking of it as a function. So that's where the application comes in. That is, when you think of the derivative existing, especially if you've had some physics, you think of instantaneous rate of change because you've got the rise over the run as the x approaches c or the delta x approaches zero. And so you get the existence of an instantaneous rate of change, especially when you're thinking about kinematics in physics. So we would like to think of that derivative as being represented by a function that can actually be a computational tool for us. So for instance, in a physics class, you might want to compute several different values of a velocity, or you might want to graph the velocity function, which would be the instantaneous rate of change of the position function. So more about that as we move through the course. Now, one thing that we've noticed is that if we want to consider the differentiability at the endpoints, just like we were considering continuity at endpoints, then we need some new notation. So again, what would it mean if we included the endpoints? Well, of course, we would get all of the derivatives existing for all C and AB, just like we have up here. But now we need a little bit different notation. For instance, for the right endpoint, we would need to approach from the left. So we just use a minus sign, which is standard, okay? And then, of course, what we're used to, normally I don't write the plus and minus, but I'll do it this time. It doesn't have anything to do with the sign of the derivative. And then, of course, if we need the right derivative, we need to approach A from the right, so we'll call that the plus. So not only do we need the derivative existing in the open set or the interior, we need the right derivative, which is this one, approach from the right, that is f prime of a plus as a superscript. And we need the left derivative as we approach b from the left, which is f prime of b superscript with a minus. Now, depending on the complication of what we get for f prime of c, these limits may be easy to compute, but formally, if we use our second description of the derivative, this would be x approaches a from the right of f of x minus f of a divided by x minus a. So it looks like this definition, but now instead of the general approaching c, x approaching c, we have x approaching a from the right. And then, of course, for the left derivative existing, we just have the limit as x approaches b from the left of f of x minus f of b divided by x minus b. So these may be simple calculations depending on the nature of the function f, okay? So what I want to do before we actually start talking about continuity in how it actually relates to differentiability, I have a computation here, and it's very simple. And I always end up simplifying things just because it's like simple is better as long as it gets the job done, but we certainly don't want to lack rigor in what we do. So what I did here is I thought, I want you to get used to the second form of the derivative. So I've taken a quadratic function here that is f of x is 2x squared plus 3x minus 5. And we're saying that our domain of definition is -2 to 3. So we're not like restricting, or we're not just having this domain because that's the best we can do. I've just restricted it. And I said here, is f differentiable on the closed set? Well, you're thinking, well, you know, this is a nice function. We should have a lot of derivatives here. So let's follow the definition. That is, first take c in the open set, -2 to 3. So by definition, we can compute f prime of c. So of course, by definition, this is the limit as x approaches c of f of x minus f of c divided by x minus c. And then, of course, we just replace f of x with its definition, 2x squared plus 3x minus 5. And then, of course, f of c is just, you know, replace x with c. So we have, again, subtract 2c squared plus 3c minus 5. Now, of course, when we subtract the additive inverse of 5, that's a plus. And so these 5s absorb in the sense that they're gone. And we're left with 2x squared plus 3x minus 2c squared minus 3c. Okay, so again, we're doing limits just like we did in the last chapter. So in order to make the wisest choice of our limit computation, we can just pair up the squared terms and the non-squared terms, as you see I've done here. So factor the 2, and we have x squared minus c squared. And then you can factor the 3, and we have x minus c. So now, when you think about it before, for instance, remember when you were doing limits and you got 0 over 0, you had indeterminate form? So what you were thinking, okay, if I get this limit, I've got a function with a whole limit. Okay, but now we're looking at the rise over run, and we're saying that this defines the slope of the tangent line where it exists. So now we have this indeterminate form, and then when we compute this and we get a limit, then we actually have the slope of the what? The tangent line. So the actual difference quotient has the whole, so to speak, as a function. If we're thinking of the function as being the difference quotient, that has the whole, but the function doesn't, right? Because f of c is defined. So this is the same thing we did before, but we're dealing with a different object. We're dealing with taking the limit of the difference quotient. So now what we're trying to do is say, okay, we think that this curve will have many derivatives, that we would be able to construct tangent lines because we're thinking about what quadratic functions look like. So now when you get to this point, you're thinking, well, this is a difference of two squares. So we have x minus c times x plus c. But now all the x minus c's absorb. Okay, so that's like really nice. So what are we left with? 2 times x plus c plus a 3, and of course 1 in the denominator. So now you're thinking, well, this is what we expected, because now this is a polynomial. And we're like, we can do this all day long, direct substitution. So we replace x with c, and we get 2 times c plus 3. That's a constant, obviously. So we get 4c plus 3. Now, you're thinking, okay, well, does this limit exist for that? Well, we can do one even better. We know that the derivative here is fine. This is defined for all real numbers. This is just 4c plus 3. That's a polynomial in c. You can't get much better than that. This has a limit for every c. So we say f prime of c exists for all real c. Hence, for c living here. I mean, we could always restrict the real numbers, so we get that for free. So now we don't have to work hard. This is automatic. When you look at this part, why I wrote automatic here is because this limit exists for any c. So especially the left limit and the right limit. So the right limit here as f prime of for instance, when we consider the derivative, so we say f prime of -2 from the right, or the what? The right derivative at -2, and then we have f prime of 3 from the left, or the left derivative of what? In this case, at 3. So the kind of idea that we're looking for here is the fact that we don't have to work hard here. We know these limits exist for all real numbers. So if we're looking for a left and a right derivative in this particular case, then we can just simply evaluate this at -2 for the right derivative at -2, and we can simply evaluate this at 3 for the left derivative at 3. So it's a no-brainer in the sense that these are automatic. So now, of course, f prime of -2 will just be 4 times -2 plus 3, which is -8 plus 3, which is -5. So that's a check. And then, well, there we go, get a check there. And then, of course, if we need the left derivative at 3, then we can simply replace c with 3. So we get what? 4 times 3 plus 3, or 12 plus 3, which is 15. And we've got that too. So the key here is that in this case, this right derivative and this left derivative may be very simple to compute. We don't have to kind of go back to the definition and redo what we've already done. We don't have to do the same computation over again. So the beauty of the differentiability on a closed set has to do with how difficult are these limits going to be to compute. If we find that our f prime of c is very user-friendly, then we don't have to go back strictly to the definition. We have f prime for any c, okay? So that simplifies these. So I don't think you always have to appeal to the definition and do work that you've already done. So that's really important. So now by definition, it is indeed true that f is differentiable on the closed set, but I don't think you had any issue with this. Quadratic functions are nice functions. Now, what's important here is that the differentiability means the existence of the tangent lines. So the curve has to have a nice shape. For instance, for smooth functions, you're not going to have holes and gaps. You can't have that. I mean, there's no way, because then you can't define the tangent line. And then, of course, if you have corners or cusps, then the tangent line doesn't make any sense. You're thinking geometrically that smooth curves or differentiable curves have to look really nice. And so you might be thinking right now about one aspect, and you might be thinking about this aspect. That is, how are continuity at C and differentiability at C related? Well, I let the cat out of the bag already. I mean, let's think about it. The smoothness is required for differentiable functions when we think about their graphs. So we're thinking, differentiability might be just a little bit step up. That is, it may produce a function that even has better qualities, because we're already thinking that a function that's continuous is really nice. No holes, no gaps. I mean, we have the limit existing, limits exist, and then we bump up to continuity, and it appears that as we move up to differentiability, we're making another improvement. So let's see what the connection is by rethinking our definition of continuity at C. You're going to find that sometimes the terminology can be tongue twisting in the sense that describing things, and it will get easier. That we often want to make sure that we precisely say what we mean, and that's okay if there's some struggle. But just remember, your notation will always kind of save you, because if the notation is good, then you have what you need to move the problem forward. So if we remember, f is continuous at C, if and only if the limit of f as x approaches C is just f of C, okay? So we're thinking, all right, well, let's just do, some smoke and mirrors here. Well, we know the limit of a constant is set constant, so let's just apply the limiting process here, just as smoke and mirrors, and then move this limit to the left side. And then, of course, if we think of the difference of limits as being the limit of the difference using the limit properties, we can write this. So by transposing here, we have a 0 left, and then we just combine the difference of limits as the limit of the difference. So now we're thinking we have an alternate characterization of continuity at C that looks like this. That is, now we can just say the limit as x approaches C of f of x minus f of C is 0. And that shouldn't be a surprise at all. That's saying the same thing. That's just basically saying the limit as x approaches C of f of x is f of C. And we already know that, but this happens to be more useful when we're trying to maybe glean certain ideas about differentiability and what it implies about continuity. So now we can think, how can we state our definition or our theorem? We're going to say, we'll go out on a limb, and we're going to say that differentiability implies continuity. So if we have differentiability at C, then that would say that we have continuity at C. So fix C element of R, and then we'll say if f is differentiable at C, then f is continuous at C, and use the alternate characterization. So you might be surprised how simple this is. It's very simple. Now, what we do in this first section is that we just get acquainted with the definition of derivative and the new symbols that we use. And then, just like with limits, as we started with the definition, we will move into some of the theoretical aspects that the definition provides. Remember, the limit definition gave us all these beautiful theorems to compute limits. And we might be thinking, we could use the definition to compute derivatives, but it might get complicated as the functions get more complicated, just like with limits. So we're going to find that the results will be very similar to what we've already been accustomed. So that'll be a big relief. Now we look at the limit as x approaches C of f of x minus f of C. Okay, so that's the new characterization. We want to show that 0, but what do we need? Again, we need to rewrite this difference in a way that utilizes the differentiability. What is it about mathematics? If you assume hypotheses that, for instance, imply a conclusion, then you must use the hypotheses in your proof, or your theorem needs to be restated. Lots of times when I teach induction, students will say, well, I proved this. And I'll say, but you didn't use your induction hypothesis. So it's not an induction proof. And that's okay. That's okay. If you can prove something with another technique, that's fine. But we want to claim that we need the hypothesis of differentiability to get continuity there. So what we do is we multiply and divide by x minus c, because that will now give us the definition or the difference quotient for the definition of derivative. So now we have the limit as x approaches c of f of x minus f of c divided by x minus c times x minus c. And then, of course, we can now apply the limit of the product being the product of limits, as long as we know the individual limits exist. And we do. We know this limit exists by hypothesis, and that's just a simple limit because it's just the limit of a polynomial. So now at this point, we have the limit as x approaches c of f of x minus f of c divided by x minus c. That is the definition of f prime of c, the derivative of f at c, which I have written here. And we can write that because we have assumed that f is differentiable at c. And then, of course, this limit is just c minus c, direct substitution, which is 0. And of course, 0 times finite is 0. So we have shown that the limit as x approaches c of f of x minus f of c is indeed 0. And by our new characterization, that gives us the fact that f is indeed continuous at c. So differentiability at c implies continuity at c. So we see differentiability is a strong condition. It's stronger than continuity. Now, one thing that's interesting that you saw in the last example was using the derivative definition to actually determine continuity or lack of continuity at a point, and then using definition to show differentiability or lack of differentiability. Now, I will say this, and I want you to think about this. This last proof that we did, I say the converse is false. Well, of course it is. And you can think of many counterexamples. You could say, well, if a function is continuous, then it must be differentiable. No, we can think of one of your favorite functions from the college algebra. That is the absolute value function. That is a nice counterexample. So think about that, because it's got the corner where it would be impossible to actually define the slope of the tangent line. That is, when you think of left and right derivatives at 0, you don't get equality of limits. And of course, if you don't get the equality of the limits, then the actual limit does not exist there. The limit of difference quotient does not exist. So this is actually very important and gives you good sources of examples. Now, let's look at the next example here that I have. And I think this is interesting because it's very straightforward. And then I want to do some other examples. But we have f of x is the square root of x plus a. This is another nice example that has really good continuity aspects. But just like with the absolute value function, there's a problem with a point in the domain. So first, we know that f is continuous where it is defined. So if we look at the domain, we know the domain here is -8 to infinity because this is where this is defined. Remember, radicals are continuous where they are defined. And so what we want to do, again, we just noted that -8 is in the domain, so we have continuity there. And then what we want to do is check differentiability at x equal -8. So now when we look at this, this is a right derivative. So we can just apply the definition. Now here, since we didn't do any calculations as we did in the last problem, we're just going to look at this by definition. So again, The right derivative at -8 would be the limit as x approaches -8 from the right of f of x minus f of -8 divided by x plus 8. So this is very simple, but this is where we're applying the definition of the right derivative directly. So f of x is just the square root of x plus 8. And then, of course, f of -8 is just replacing x with -8. So we have the square root of 0 here. So that goes away. And then, of course, downstairs, we have, in this case, x minus a -8, which is x plus 8. So now when we look at this, we have x plus 8 to the 1/2 power divided by x plus 8, which will simplify to 1 over the square root of x plus 8. And now we go back to infinite limits, which we studied in the previous lecture. That is, now as x approaches -8 from the right, we see that this defines a vertical asymptote. That is, this is a 0 here of the denominator, which is not a 0 of the numerator. So this defines a function that becomes unbounded because now x equal -8 is a vertical asymptote. And then, of course, as we approach from the right, the value of the radical is positive. So we affix the positive sign, or just we say infinity. So now we see that we have an infinite limit, which is what we can describe as unbounded, but it's not a real number. So this is not a surprise, because when we think of x plus 8, we're just thinking of the standard quadratic function shifted to the left by 8 units. So when you think of this, you can draw it. So again, just -8 here. And we'll just think of, again, just drawing a sketch here. Something like this. And so now what we have at -8 is the existence of what we call a vertical tangent. Vertical tangent line. Now, we know the slope of a vertical line is undefined. I mean, we can draw it. We think about other curves where we have vertical tangents. This is not surprising at all. So when we consider the quadratic function, we're like, man, this is a nice function. It doesn't have vertical tangent lines. They just don't exist. You think of a quadratic function as just being smooth and no problems at all. No issues with domain. That was a very simple calculation. At least it was not surprising. And so now as we approach -8 from the right, we see that we have a problem here. Even though we can draw the graph, the slope of the tangent line becomes infinite. And in the limit, we don't have a well-defined real number. We have infinity. But that doesn't keep us from drawing infinite tangents. So at least we know the behavior. We know the behavior. So strictly speaking, the derivative of f, in this case at -8, does not exist. But we can still sketch this line in the sense that we know now the behavior and why the graph just turns to the point to where the slope is infinite. That is, we now have a vertical tangent. So this gives us much indication as to why we have always drawn square root functions that look like this. Again, at the time, you might have thought, well, we just plot a bunch of points and we see, but now the characteristic of the graph is dictated by the lack of differentiability at -8. Again, we did not see that with the right and left derivatives that we computed for the quadratic function. And we didn't even have to use the definition because we had the derivative existing all over the place. So that was no problem. Here, we just went straight to the definition And again, because we're just investigating differentiability at -8. Now, if you wanted to look at differentiability otherwise, then you could now just apply this to this particular function and let X approach C and see what you get. So the key here is sometimes we refine our arguments to focus on specific points. Sometimes they're more general, so we're just looking into the horizon to see what are the values of X for which the function has what differentiability, for which the function has the tangent line. Okay, so every time we have a point of differentiability, we have a tangent line. We can draw the tangent line. We have the instantaneous rate of change, of Y over X. And of course, that's going to mean that we can have different notations that will be very useful, especially you will find so in your physics classes. Now notice here, F is not differentiable at -8. And then I wrote this again. The derivative at C represents the slope of the tangent line to the graph of F, provided the limit exists. I can't say that enough. Geometric intuition is important. And we want to be able to classify the arithmetic that we compute geometrically, because that is important to us. Now, there's a very interesting result here that I want to give you, and we'll do another computation. But this is something I always share with my calculus students, and I always come up with a different proof and try ways to simplify things. Only because when you think about things, for instance, as I come up with new identities, as I teach mathematics and new results, I always like to work with them and reformulate them. So one thing that you'll find in your homework is there appears to be a connection. The problem doesn't state specifically what I'm stating here, but you start with an even function, and somehow they're trying to say that will tell you something about the derivative. You start with an odd function, and somehow that should kind of tell you something, what to think about the derivative. Well, maybe, maybe not. So oftentimes, as I read a textbook, I will see glimmers of a particular result that's theoretical. And so what I'll do is I'll take the result and make it more general. Because many times in mathematics, you don't want to just think, well, it appears that it would be that way, so that makes sense. But that doesn't help you, because that's not going to be of assistance in the future when you see the same concept again and you've done nothing to iron it out. So here's the actual theorem that I've constructed. Suppose F is a differentiable function. We're just going to say it has some derivatives for a set bigger than a single point. And we're going to assume, and what I'm doing, I'm proving one. You can prove two with a similar technique. I'll say if F is an even function, then the derivative F prime is an odd function. How fascinating. I mean, it's true. And then, of course, if F is an odd function, then F prime is an even function. Now, what I did over here is I just reminded you about the definition. So if F is even, then if you have X in the domain, you have its additive inverse. So the domain must be symmetric relative to the origin. And then you have this nice little algebraic fact, F of the additive inverse of X is just F of X. The negative, so to speak, absorbs, and you get a function that has symmetry relative to the y-axis, or y-axis symmetry for short, because we have too many words here. And then, of course, if F is an odd function, you have the same symmetric domain, but now you have F of the additive inverse of X is the additive inverse of F of X. Okay, so that's a neat result. Now, I've had students in the past say, well, can we use this theorem to prove this result? And as we learn more theoretical results, there will be simpler proofs of this. But what I thought was interesting is that with what we have, we just have the definition of derivative. So I thought, well, let's just look at this using the definition of derivative. So now here's our proof of number one. Notice what I said, f is even, we're assuming that. And so of course, if we take C in the domain, then we know the additive inverse of C is in the domain. Now what I've said here kind of sums up everything. What we want to do is show if f prime is indeed odd, then f prime of the additive inverse of C should be the additive inverse of f prime of C. If f prime is indeed an odd function, the negative factors. So that kind of kills two birds with one stone, so to speak. That is, the set of differentiability is symmetric, because if we get the differentiability at C, then we automatically get the differentiability of the additive inverse of C. So the key is we use the fact that the differentiability has to kind of trickle down from the hypothesis. So if it doesn't work, then those 2 points get kicked out and we still have the symmetry. So the key here is we simply need to show, as I've said here, that if we compute the derivative of f at negative C, or the additive inverse of C, we actually get the additive inverse of f prime of C, because once we establish that derivative exists, then we have those 2 points and we're good to go. So it's kind of like the definition of derivatives. Derivative carries us through this proof. Now, you might find this a little bit smoke and mirrors, but what I tried to do here was change the proof without having to actually change variables, which I've done before. So I made some corrections here as I wrote this out. I had a student come by, and as I was talking to the student, I thought, well, this might be a simpler way to do this in my mind's eye. So I think you'll like this. So by definition, we have f prime of the additive inverse of C. So again, we say limit as x approaches the additive inverse of C of f of x minus f, again, C's been replaced with the negative of C, or additive inverse. So we have f of negative C, and then we have x minus the quantity negative C. So I'll just say negative for additive inverse so it doesn't sound so long-winded. So now here I'm going to use the fact that f is even because it is. So the negative here absorbs, right? F is even, so we use that, okay? And now we're good to go. F minus the negative is just f plus. Now I have my little change of variable here, but it's a little bit easier to use. I simply want to replace x with negative x, because now I can be able to use the little toggle that we used before. Notice if I replace x with negative x, I get negative x approaching negative C. But of course, by multiplying that result by -1, that just simply is equivalent to x approaching C. So like if you say negative x approaches -2, then the additive inverse of x approaches the additive inverse of -2, which is 2. So that toggle is kind of like what we did many times before. It just very, very convenient. So now we have, again, the negative x approaching negative C can now be replaced with x approaches C. Of course, x is replaced with negative x, and we do the same thing down here. But of course, here we go again. F is even, so the negative absorbs. But downstairs, we have to factor the negative. So we have the negative of the quantity x minus C. And then, of course, that negative is factored because we know we can factor constants with limits. So now we have the additive inverse of the negative of the limit as x approaches C of f of x minus f of C divided by x minus C. This is just f prime of C. So we have the negative or the additive inverse of f prime of C. So this proof, even though it's a little bit more complicated than using another theoretical result, which we will have down the road, it is certainly using what we already know. And so I would encourage you to look at the proof for 2 using similar techniques. And then, of course, now you'd be using the fact that the function is odd to show that the derivative is actually even. Now, of course, by definition, f prime is an odd function. So now you can have in your mind's eye, when you think about even functions and odd functions that you learned about in pre-cal and cal, as you start taking derivatives, you're like, that's an odd function because I started with an even one. Okay? There will be many times when you will know how to characterize the original function due to your experience in the prerequisite courses. So this will be a good way to check your differentiation process. Now, clearly, not all functions possess even or odd. I mean, that's fairly restricted, but you do know some really important functions that share these properties, mainly some trig functions. So it's going to be interesting. And plus, the polynomials give us all kinds of even and odd examples. So this will be really interesting as you start taking derivatives. So that's good. That's an interesting result. Now, what I want to do is just look at a simple calculation, 2 simple calculations utilizing the definition of derivative. Now, as I've written here, because I can't seem to stop myself, just reminding you, the graph of a differentiable function is smooth. No corners, cusps, holes, gaps. We say smooth curve in differential geometry. So when you study curve theory, you want your curves to be nice. Okay, you want your surfaces to be manifold. You've got all kinds of beautiful calculus going on. So you gotta deal with surfaces and curves that are well behaved and beautiful. Okay, so again, you know, the existence of the calculus is great. I mean, if we just want to focus on sequences and you know, functions that are disturbed and pathological or whatever, that's kind of fun, you know, but we also want to look at the beauty of the calculus where we can actually look at functions that have beautiful properties and allow us to do infinite numbers of derivatives and create Taylor series and Maclaurin series and Fourier series. So we like the fact that our derivatives exist. So what I've done here, this is what you'll see in some of your homework, and it's very straightforward. That is, it says compute an equation of the tangent line, and actually is what we need there. Let me fix that. Compute an equation of the tangent line to f of x, which is 8 divided by x minus 5 at the point 13, 1. Now, of course, lines are not unique. You can multiply them by any constant and change them. So the equation of the tangent line is not unique. That's why we say an equation. Now, this is just to give you some practice. Clearly, 13 is in the domain of f. Okay, and then of course, if you substitute 13, you just get 8 over 8. So that is indeed a point. I mean, it's always good to make sure the point you have is actually valid, but that's very simple. So what's a tangent line? Well, if we have a point, we think about algebra 1, we need a slope. So we can always figure out the slope of the tangent line using the definition of derivative. And then we can use point slope to construct an equation for the tangent line. So this is a very common occurrence in the calculus. That is, as you learn how to differentiate new functions, you do a tangent line calculation. And I guess it gets kind of boring and maybe sometimes not very interesting. But as we move into calculus 2 and we study curves and parametric representations, we're going to find a way to actually compute the Cartesian derivative from parametric representations. That is, when we take derivatives of the parametric representations, we're going to figure out a way to combine them so that we actually get the standard Cartesian derivative. So there'll be applications of tangents and all that won't be as dry. So you can look forward to that. Now, applying the definition, and this is why I love this alternative form. It's so much more clean and effective. So we have f prime at 13. The derivative of f at 13 is now the limit as x approaches 13 of f of x minus f of 13 divided by x minus 13. Now, of course, we simply do the replacement. F of x is 8 over x minus 5. And of course, f of 13 is 1. So that's convenient. And of course, we have x minus 13. Now, what we want to do is compute the limit. We know it's indeterminate, so we want the problem to go away. We want it to absorb. So first, we have the x minus 5 here, so we get a common denominator. So we have 8 minus the quantity x minus 5 divided by x minus 5, all divided by x minus 13. And of course, you know what's going to happen. We simply do the arithmetic here. So now we have the 8 plus the 5 when we distribute the negative, and that gives us a negative x plus a 13. And of course, this will collapse. We just bring the x minus 5 down with the x minus 13. The x minus 13 we reciprocate, and so they join, so to speak. That's really what's going on, but we just get a nice collapsing. So now you're thinking this will absorb if we just go ahead and factor the negative. So we factor the negative here, and we have the quantity x minus 13, and we have an x minus 13 here. So now, of course, these absorb. Calculus is very nice. I mean, the calculations are rewarding and fun to do. So now, just like doing the process back in the first chapter, we now feel good about the fact that the tangent line will exist because we know its slope will exist. So now, of course, we're just left with the negative of the limit as x approaches 13 of 1 divided by x minus 5. So this is direct substitution, just a rational expression, direct substitution. So replace x with 13. And of course, 13 minus 5 is 8. Then with the negative, we have negative 1/8. So there will be theorems that we're going to learn that will allow us to compute derivatives based upon the form of the function. And just like the form of functions with limits, we have certain properties, you know, limits of products or products of limits, etc. We're going to have similar theoretical results for derivatives. So we have that to look forward to. And they'll be quite fascinating. So now we have the slope and we have the point. So we just do the point slope formula. So in this case, we have y minus 1 and the slope negative 1/8 times x minus 13, the x coordinate of the point. So now if you want, go ahead and distribute the negative 1/8 to give us negative 1/8 x. And then, of course, the negative here absorbs this negative, and we get 13 over 8. And, of course, we transpose the 1. So now, of course, 1 here is just 8 over 8, common denominator. So 8 plus 13 is 21. So we get y is equal to negative 1/8 x plus 21 over 8. And that gives us an equation of the tangent line. Now, of course, what you're going to find is that in some cases, the problem will kind of necessitate the slope-intercept form. It'll have y equal and then a box where you fill everything in. Of course, if that's the case, just transpose items so that you get this form. And again, this is a common calculation in calculus, especially when you learn the definition of derivative, as I've said before. So get used to it. It's not half bad. Now, the very last example has to do with the conjugate method. And I did speak about this function earlier, but I was only looking at it, as I said, with the left endpoint. You know, we thought about you're doing the right derivative as x approaches negative 8. So when we look at this and we think about it, we just want to do a standard calculation that is basically if we're just looking for the existence of where the derivative is, for which values of x do we have a derivative. And I think you're at this point thinking as long as we avoid the negative 8, everything else should be fine, just thinking about the curve. So we're just going to attack this problem as finding the set of differentiability. So now we think about the domain, which is -8 to infinity. So now we consider the open set. We know what the case is at -8. So we've got f prime of c for c in the open set. Limit is x approaches c of f of x minus f of c divided by x minus c. So now we just simply substitute. Remember, before we were just substituting in -8 and it simplified everything really well. Now we don't have that luxury. So we got to work a lot harder. So we have f of x, which is the square root of x plus 8, and we have f of c, which of course is the square root of c plus 8. That's one thing that's nice about this particular formula. The delta x is fine, but this does simplify some of the algebra, and arithmetically, it's just better. So now we're back to the methods of the previous chapter. We have indeterminacy. That is, we have 0 over 0. So how can we fix that with square roots? Well, we can do conjugate method. So we can multiply and divide by the sum of these square roots. So if you like here, this is the conjugate method. Conjugate method, which again is our mainstay when it comes to radicals, especially square roots, and then of course to trig functions where we have no other source of algebra. So now, of course, now we have the outer and the inner absorbing because this is just a factor difference of two squares. So we have the x plus 8, which results from the multiplication of the two radicals. And then we have the additive inverse of c plus 8, which is the result of multiplication of the two radicals. So that's a beautiful result. And then, of course, downstairs, we have the sum of the radicals times x minus c. Of course, we leave that alone because what's the whole idea here? We want to absorb the x minus c. If we can get rid of that, then we know that we've got a limit. So now, of course, this is simple. The 8's absorb, and we have x minus c, and we see that these two expressions absorb. And so now we've got something that we can use direct substitution. So we have the limit as x approaches c of 1 divided by the square root of x plus 8 plus c divided by the square root, plus c plus 8 square root divided by 8. Amazingly, just take the sum here and do 1 over it. That might be an easier way to talk about it. Now with direct substitution, this is a constant, right? So we just replace the x with c. So we have the square root of c plus 8 plus the square root of c plus 8. So that's 2 copies. So we have 2 times the square root of c plus 8. So at this point, direct substitution. Remember, algebraic functions, radicals, etc., are continuous where they are defined. So that's what allows us to do these nice direct substitutions. And that's all we have to do here. You can think about this as the limit of a quotient, but it's easier just to go forth with the direct substitution. Theoretically, sometimes we need to focus on the limit of the product, like we did with differentiability implying continuity. There's theoretical significance to doing that. But when we have this, direct substitution is just the quickest way. And so now we look at this and say, okay, this gives us the definition of the derivative where it actually exists. And so, of course, that just means that we avoid -8 and get anything bigger. So C larger than -8. And so now, like I said before, we now know that we have a machine to give us the slope of the tangent, the instantaneous rate of change of y over x. Okay? Change in y over change in x instantaneously at the point. And so what we normally do when we're using the alternative definition is we simply just replace the c with x. And now we have a machine that will give us the derivative for any value. Of course, these are basically saying the same thing, but we're more we're more interested in probably using a value or a variable of X, but not necessarily. You're just going to find that as you do computations, X's and Z's and T's will be more popular. So in order to write this as a function, we could just say, okay, switch out the C with X, and now we have f prime of X as a function is just 1 divided by 2 times the square root of X plus A. So like I said before, you can think of computing f prime of C with the second type of derivative formula and then doing this process. And it actually works out very nicely. So again, just remember, we have to use letters, we have to use numbers, and we have to try to be consistent with those usages. So when we define the definition of derivative at X equals C, then we use C, obviously. Okay, so how you want to express the function is usually up to you. But when you're doing a homework exercise, if the function is given in terms of X, and then they're saying write f prime of X. Okay, all right, so that's telling you if you write the derivative, you write it in terms of that variable. So if you do this computation, then you switch out and you do this. Or maybe you had f of t, and t is approaching c. Okay, so you need to write f prime of t. Just remember, use whatever variable is part of the problem. And of course, those of you that have had some physics and have studied that, or any kind of chemistry class or science or engineering, you understand that usage of the variables that are given are important, because many times the variables carry with them definitions, and they're chosen to maybe give some idea as to what they represent. So as you're working through the definition of derivative, look at the original definition with the delta x, and then look at the definition that the alternative definition. And as we work through the course, we're going to find that alternative definition has arithmetic or arithmetic qualities that are very, very useful and actually easier to use at many times, as you've seen in these calculations. So as we continue through the lectures that are upcoming, we will talk about how the definition of derivative gives us theorems to compute derivatives that will make our life easier. But then the goal is going to be like, okay, well, we did the sums, we've done the, for instance, differences, we've got some derivatives of some trig functions. Then maybe we'll think about derivatives of products, derivatives of quotients. Is there something that can be useful? So we don't have to go through all of this algebra every time. And we're thinking that'll be good, but then we think about back into limits and continuity, composition results, right? We have the limit of a composition, which can also be tailored right into the continuity of a composition. So basically the same result. So we're thinking we're going to need to know how to differentiate the composition of functions that are differentiable. And that's going to be a major result. So we do the same things with the derivatives that we've done with the limits and the continuity, because that's what we do in calculus. So what makes all of this work? The function. The function is by far the most important abstraction in mathematics, because we operate on functions. And so we just have to make sure that our notation is consistent, and we'll just continue to do that. So I hope you've enjoyed the definition of derivative. I think this is very fascinating, and we'll take it as far as we can go. And then once we exhaust that, we'll talk about antiderivatives and maybe areas and the Riemann integral. So it's gonna be a quick process, but a very enjoyable one. So thank you for your time. We'll see you later.